We've talked a lot about why carbon is so awesome for life, and a lot of it comes out of the fact that carbon tends to form 4 covalent bonds. And that comes out of the fact that carbon has 4 valence electrons. A neutral carbon would have 6 electrons, same as its number of protons, and the 6 here tells us the number of protons. Neutral carbon would have 6 electrons. 2 are in its innermost shell, which leave 4 for its outer shell. And those 4 in the outer shell, those are the electrons that tend to do the reacting. We call them valence electrons. And so, for example, if you wanted to bond with 4 hydrogens, the carbon could contribute 1 electron to each of the 4 bonds, and then each of the hydrogens could contribute. Each of the hydrogens could contribute an electron, and then they both feel like they have full outer shells. Hydrogen is just trying to get to 2 electrons in its outer shell. It's trying to get to a stable configuration like helium, at least when it comes to the electrons. And carbon is trying to get to a stable configuration like neon. And now carbon can pretend like it has 8 electrons. It's sharing these 8 electrons, and each of these hydrogens can pretend like they have 2 electrons. But this makes carbon very well suited for 4 covalent bonds. You see this methane right over here. I have it redrawn right over here. But it's not just bonding with hydrogens. It can bond with other carbons. It can form these hydrocarbon chains. It can bond with oxygen. It can bond with other things. And so you might say, all right, I can buy that carbon is good for life. I understand why life as we know it is based on carbon. But I see other elements here that have 4 valence electrons. And in particular, the one that's closest to carbon on the periodic table is right here. Silicon. Silicon has 14 electrons. It has 14 electrons, but you have 2 in its innermost shell. I'll just draw them like that. They're buzzing around in its innermost shell right over there. Then you have another 8 in its second shell. So 1, 2, 3, 4, 5, 6, 7, 8 in its secondmost shell. So I've used up 10 so far. That leaves 4 in its outermost shell. 1, 2, 3, 4. So silicon, like carbon, it has more electrons. It has 8 more electrons, but its outermost shell has 4 electrons, and those are the ones that tend to do the reacting. So silicon also has 4 valence electrons. So let me draw it like this. I'm using blue for silicon, so let me put blue. Silicon, if I want to just draw its valence electrons, it also has 4. It also has 4 valence electrons. And as you might have guessed, silicon does tend to form 4 covalent bonds. And so you might say, okay, well, I could imagine life that is based on silicon. And if you have done that, you are not alone. This is a picture from the 1967 The Devil in the Dark episode of Star Trek, where they imagined a silicon-based life form called the Horta. And science fiction theorists and writers have always said, well, you know, silicon seems close to carbon on the periodic table, has 4 valence electrons, it tends to form 4 covalent bonds. Maybe you could have silicon-based life. But when you dig a little deeper into the chemistry, it becomes less and less likely. I don't want to rule anything out. I'm sure the actual universe will surprise us and give us things that we can't even start to imagine. But when you start to think about silicon, at least in terms of life as we know it, the chemistry isn't as favorable as carbon. For example, carbon can readily bond to itself. Carbon-carbon bonds are reasonably strong enough to form these hydrocarbon chains, and they can get much longer than this, while silicon bonds are not that strong. So you're not going to find the analog of hydrocarbons. You're not going to find long chains of hydrosilicons, I guess you could say. So that's one ding for silicon. The other ding is, this right over here, this is methane, and silane, in theory, can be around, but it does not readily form. Silicon does not readily bond to hydrogen. This isn't that likely. And then the last one, you have carbon dioxide, which is obviously key for life, and silicon oxide is actually very common. But the problem with silicon oxide is it doesn't typically act as it's not typically in a gaseous state, at least at temperatures where we're used to dealing with life. Most of the silicon oxide on Earth is in the form of quartz. like that. Or it's a major component in things like glass or sand. It is in a solid form. And a big part of carbon dioxide, what makes carbon good, not only does it tend to bond with four things or form four bonds. In this case, it's forming two double bonds in carbon dioxide. But those bonds are strong enough to form chains like this, but they're not so strong that they can't participate in a lot of chemistry, in a lot of chemical reactions. While silicon oxide, this is very strong. This is a very strong bond here, and it's hard for silicon oxide to readily participate in chemical reactions the way that carbon dioxide would. Also, carbon dioxide can be dissolved in water, while silicon oxide it is not soluble in many things. So even though silicon starts to, it's got the four valence electrons, it can form these four bonds. From there, it starts to become a little bit harder to see how it could actually be the basis of life. But, I encourage you to keep thinking about how it could be. Maybe, planets with different temperatures or different pressures or different conditions. Who knows?